One thing to notice here is that near the local minimum, you have negative slope and then a slope 0 and then positive slope. And also near the local maximum, you have positive slope, then slope 0, and then negative slope. And that's something to look for when you're trying to locate local extremes. If the slope changes sign, then that's a sign that they're of a local extreme at that point. Okay, so let's do some more definitions here. Function f of x is increasing on an interval if f of x1 less than or equal to f of x2 for all pairs of points x1 and x2, and the interval satisfying x1 is less than x2. And function f of x is decreasing on an interval if f of x1 is greater than f of x2 for all pairs of points x1 and x2 such that x1 is less than x2. And then the increasing decreasing theorem. A function f is increasing on intervals where the derivative is positive and decreasing on intervals where the derivative is negative. So here we have an example here. This is actually a local maximum value here. And we have a positive slope on the left, and then we have negative slope on the right. So negative slope means the function is decreasing. Positive slope means the function is increasing. So we have what's called the first derivative test that's based on this increasing decreasing theorem. The first derivative test, let c be a critical number of a continuous function f, which means that either f prime of c is 0 or it's undefined. If f prime changes from positive to negative, then f has a local minimum. So we have positive slope and then negative slope. If it changes from negative to positive, it's a local minimum. Positive to negative local max, negative to positive local minimum. If f of x keeps the same sign, then f has no local extreme value. So if we have positive, it looks like perhaps undefined slope. It gets pretty steep there, and then it's positive slope again. So it could be a critical number without being a local extreme. Okay, so we can also, the second derivative also tells us something about the graph. On intervals where the graph where the function lies above its tangent line, f is said to be concave up. That means that it holds water. Go back to this function here. So near these local minimums, the function is concave up. It holds water. Near the local max is concave down. That spills water. One way of defining concavity is in terms of the tangent lines. On intervals where the function lies above its tangent line, the graph is said to be concave up. On intervals where the function is below its tangent line, the graph is said to be concave down. So if you draw the function at this point here, here's the tangent lines here. I'm drawing a couple of tangent lines. This is the tangent line is below the, except for the point where it touches, the tangent line is below the graph. So that's concave up, it holds water. And this one here, except for the point where it touches, the tangent lines are above the function. That's where it's concave down, that's where it spills water. Okay, so there's another test called the second derivative test. Let f be a continuous function near c. If f prime of c equals 0, and if the first derivative is 0, and if the second derivative is less than 0, then f has a local maximum. That means it spills water. That means there's a local maximum there. If f first derivative is 0 and the second derivative is greater than 0, then f has a local minimum. So that's the second derivative test. Usually I find it in terms of looking local minimums and maximums, I find usually the first derivative test to be more helpful. But the second derivative, sometimes, occasionally it may help with that also if it's difficult to apply the first derivative test. But I mainly use the second derivative to determine concavity. So that's sort of one of the more subtle features of the graph, is whether it's concave, whether it holds water or spills water. Okay, so here we have an example, and we want to analyze the graph of f of x. This is a polynomial function. And okay, so we can take the derivatives. So f prime of x, the exponent, this is 4x to the third plus 21x to the second minus 24x. The exponent comes out in front, and then you take 1 away from the exponent, so it's 4 times 3 is 12, x squared plus 42x minus 24. So this is a quadratic polynomial. We can try to factor this. I think I'll factor out to 6. So it's 6 times the quantity, 2x squared plus 7x minus 4. And we want to know where this is equal to 0. We might be able to factor it. Let's see if we can factor it. 2x times x gives us a 2x squared. And then we need two numbers multiplied to negative 4. Outer product plus the inner product has to be equal to positive 7. So I would say put a plus 4 here and a minus 1 there. I think that'll do it. You can check with the FOIL method. 2x times x is x squared. Outer product is 8x. Inner product is negative 1x. Combine those to get 7x. Last times last. Negative 1 times 4 is negative 4. So if it can't be easily factored, you can always use the quadratic formula. With a is a number in front of x squared, b is a number in front of x, c is a number by itself. It's a quadratic formula is x is equal to minus b plus or minus square root b squared minus 4ac over 2a. But oftentimes it's quicker to factor it. But if it's hard to factor, then use the quadratic formula. Okay, so then we can use the so this is this would be a and b, and c. Okay, so use the zero product rule. So either 6 is equal to 0, or 2x minus 1 equals 0, or x plus 4 equals 0. And you'll get this 6 is not 0, so you'll have two solutions. Add 1, divide by 2, you get x equal 1/2, or x equal negative 4. So at 1/2, so if x is less than half, for example, if x is 0, you're going to have a negative times a positive, which is negative. And if x is between a half and 4, for example, if x is 1, you'll have a positive times positive, which is positive. And if x is more than 4, did I do that right? X is 0 minus if x is more than 4, for example, 5. Oh, you know what? This is negative 4. I knew something was wrong here. Minus 4. X equals minus 4 here. So if x is less than negative 4, for example, negative 5, you'll have negative times negative, which is positive. Okay, so so here at 4, you have function increasing, then it's 0, and then it's decreasing. So that's a local max. I'll just write max, but it's a local max because I'm running out of space here. At this point here, at the other critical number, you have negative slope, and then slope 0, and then positive slope. So this is a local min. So that, anyway, that's good information for the graph. The second derivative, take the derivative of the derivative. So the first derivative is the derivative of the first derivative, which is 12x squared plus 42x minus 24, and that's going to be 24x plus 42, and we want to know where that's equal to 0. Okay, so yeah, we could divide everything by 6 here. So we have 4x plus 7 is equal to 0, and that means x is equal to negative 7/4. So we're going to have an inflection. This is called an inflection point, where where it changes concavity. So it's negative 7/4. It's the second derivative is equal to 0, and then if x is more than negative 7/4, for example, if x is 0, this is going to be positive. If x is less than negative 7/4, for example, if x is negative 2, this derivative will be negative. Okay, so so we have this is concave down, it spills water, and there's a concave up, it holds water, and the point in between is called an inflection point, where it changes concavity. Okay, so that's good information for the graph. It's also helpful to get the intercepts. If we go back to the original function, see if we can find some intercepts. Those are often good to know, and oftentimes important for applications. So the intercepts, let's say, well, that y-intercept is f of 0. F of 0 is going to be 0, so that's the y-intercept. So that so the y-intercept occurs when x is 0. X-intercepts, you want to solve f of x equals 0. So you want, that's when x-intercepts occur when y is 0. So we have 4x cubed plus 21x squared minus 24x equals 0. So we have a common factor of x. Okay, so we'll factor that out. So x times the quantity 4x squared plus 21x minus 24. So that we could try to factor this, or maybe use the quadratic formula. let's see what happens if we try to factor it. The middle term is even, so it's not going to be 2x times x. We might have a 4x times an x. But to get the 4x squared, we either need 2x times 2x, or we need 4x times x. And 2x times 2x would give us an even middle term. So let's try the 4x times the x. And then we need two numbers to multiply. Well, the outer product has to give us, plus the inner product has to give us 21, but they have to multiply to negative 24. So let's say 8 times 3, 6 times so let's see, have to be positive times negative to get a negative 24. So let's say negative 1 times 24, negative 2 times 12, negative 3 times 8, negative 4 times 6, negative 6 times 4, negative 8 times 3, negative 12 times 2, negative 24 times 1. So 4 times the one number plus the other number has to give us 21. 4 times 8 is 32, minus 3 is 29. 4 times 6 is 24, minus 4 is 20. Yeah, I don't, 4 times, yeah, I'm not seeing what combination might work there. So let's try the quadratic formula. So in the quadratic formula, we have a is the number in front of x squared, b is the number in front of x, c is the number by itself. So x is going to be minus b plus or minus square root b squared minus 4ac over 2a. So it's going to be minus 21 plus or minus square root 21 squared minus 4 times 4 times negative 24 all over 2 times 4. And it's minus 21 plus or minus square root 441 plus 16 times 24. 384. Over 8. Minus 21 plus or minus 441. 5, 12, 825. Okay, so square root of 825. Yeah, so let's say 30 squared is 900. So it's it'll be close to 30. Let's maybe 28 or 29. Let's try 29. 29 squared. And then right 81. 2 then right 18, 26, 58. 1, 14, 841. So that's pretty close. So let's say approximately 29. So it's approximately equal to negative 21 plus or minus 29 over 8. Minus 21 minus 29 is going to be negative 50. So negative 50 over 8. Or negative 1 plus 29 is 8. 8 over 8. So this is approximately 8 into 50 goes, well, 6 times 8 is 48. So it's approximately, let's say, negative 6 or 1. So then we can plot some points and sketch the graph. So we have the intercepts -6, 0, and 1, and then we have the this is a local max. There's no absolute min or max, but there's a local max here at -4, and there's a local min here at 1/2. I'm not writing the word local, but it's supposed to be local. It's not an absolute min or max. It's a local min or max. And then we have the inflection point here. Is where it changes concavity. And then we have the 3 intercepts. So you plot those points. So this is where the inflection, where it changes from going from spilling water to holding water at this point here. And you have the 1, 2, 3 intercepts. And you have the local max and local min. Local there's a local min here. Okay, so that concludes this presentation.